And so, several years ago, I worked with a set of young people. They're all at least half my age. Most of them are 1/3 my age. I'm in my 70s, and these people are in their 20s mostly. And it's wonderful. I've retired from Caltech. I no longer teach. I no longer have any responsibility for these students. The person who's responsible for them is Yanbei Chen, who has replaced me, leading what used to be my research group. And I get to work with them as though I was a postdoc. This is a wonderful way to work. We have a collaboration that consists of 2 people at Cornell in this particular work. There are 6 at Caltech, 1 in South Africa, Jean-Drew Brink, and myself. And we collaborate by video conference. And I am usually traveling, so here I am alone in a video conference. And this is Cornell, this is Caltech, and this is South Africa. And we have a series of papers coming out in Physical Review D. The first 3 are on the archive. 1 is published. And there was a Physical Review letter last year that described the things I'm going to present to you in the next few minutes. So what I want to do is describe our new way to visualize the space-time curvature in a black hole collision. Let me begin by reminding you what happens in electromagnetic theory. When we slice space-time into space plus time, for example, in flat space, you choose an inertial reference frame. Then the electromagnetic field tensor, which is a second-rank antisymmetric tensor, it gets decomposed into the electric field and the magnetic field. And we visualize these by the integral curves of these fields, that is, by field lines. And these field lines are very powerful tools for understanding what goes on. For example, the magnetic field, the dipole magnetic field of the Earth is a concept that you have all seen used in powerful ways. Well, similarly, in general relativity, when we slice space-time to space plus time, the central mathematical object, which is called the Riemann curvature tensor, it breaks into 2 parts. Something that is rather like the electric field and something rather like the magnetic field. But in this case, these are symmetric trace-free tensors. I'm doing this all in vacuum. So 2 symmetric trace-free tensors. One is the space-time part of the Riemann tensor. That's the electric part. The magnetic part is basically, this is taking like a cross product. So it's a Levi-Civita tensor. And it picks out the space-time part. So those are technical details that are not important. The important thing is the physical nature of these fields. So this electric light field describes tidal accelerations, like the tidal field of the moon that raises tides on the Earth's oceans. If you have 2 freely falling particles, they're separated by some separation vector. One is at location Q, the other at P. Then this tidal field, E, it produces a relative acceleration of these 2 particles. And that relative acceleration is minus this electric part of the Riemann tensor contracted into the separation vector. Or think of this as a matrix multiplied by the separation vector. And so, because this produces the relative acceleration of particles, we call this the tidal field. Similarly, it turns out this other piece of the Riemann tensor describes differential frame dragging in this sense, that if I put a gyroscope at the location of particle P, and I measure how it precesses relative to inertial frames at Q, there will be a precessional angular velocity as seen in inertial frames at Q. That precessional angular velocity is just the product of B with a separation vector. So very simple physical explanation of these two objects, these two pieces of the Riemann tensor. This will, in all future textbooks on relativity, this will be a central part of them. But somehow this has not been a central part of textbooks until now. So let me talk about visualizing then this tidal field. Any symmetric trace-free tensor is completely characterized by three orthogonal eigenvectors and their eigenvalues. This is just elementary matrix mechanics, linear algebra. So for the tidal field, you pick one of these eigenvectors and you build its integral curves in the same way as you take the electric field and build its integral curves to get an electric field line. It's the curves that are tangent to this vector. We call this a tendex line. Tendex comes from Latin. Tendere means to stretch. The eigenvalue associated with this is called the tendicity of this field line. For example, the Earth has a set of tendex lines, three orthogonal families of tendex lines. There are these red lines that are tangent to the eigenvector, which is the unit radial vector. That is one of the eigenvectors of this tidal field. And what this means physically is that if a person hangs or floats, say, in the space shuttle, with her feet pointed toward the Earth and her head here, she will be stretched along that field line. But if she is oriented tangentially to the field line that points in the theta direction, she will be squeezed. So the tidal forces, in the case of the Earth or the Moon or the Sun, is a stretching toward the gravitating body, a squeezing in tangential directions. And this is described then by red tendex lines that stretch and blue ones that squeeze. In fact, the relative acceleration of head and feet is just the tendicity of this tendex line multiplied by the height of the person. The person is twice as high. A 2-meter person gets stretched with twice as large an acceleration as a 1-meter person. Now, if we have a non-spinning black hole, the tendex lines are the same as for the Earth. But for a spinning black hole, a fast-spinning black hole, this is a black hole with something called A. The dimensionless spin is 95% of the largest spin a black hole can have. In this case, rather remarkably, the tendex lines near the black hole, blue squeezing tendex lines come out of the North Pole and go back into the South Pole. And red lines come out of the equatorial regions. So it's very different. This was not understood until about 2 years ago. We can also define a horizon tendicity. This is for the horizon of the black hole. So I have the horizon of the black hole is colored here. It's not black, it's really black, but it's colored. If a person is oriented perpendicular to the horizon, she gets stretched if she's above a red part of the horizon. She gets squeezed if she's above a blue part of the horizon. And the tendicity is the normal, where n is the unit normal to the horizon. It's the normal component of the tidal field. A region that is very red has a large horizon tendicity. We call that a horizon tendex. So there's a a stretching horizon tendex that goes around the equator of a black hole and squeezing tendexes at the poles of the black hole when the black hole spins. Strangely, this has not been previously understood. You were always told that if you fall into a black hole radially, you get stretched. That's not true. If you fall into the north pole of a fast-spinning black hole, you get squeezed. And the tendex lines that have large tendicity, a collection of tendex lines with large tendicity, we call a tendex. It's a three-dimensional tendex. So there's a three-dimensional tendex comes out in the shape of a fan around a spinning black hole. And there is a three-dimensional tendex, large tendicity, that comes out of the north pole, swings around into the south pole. And these tendexes are very important. That's where the energy associated with the spin is, where you have large tendicity. We do the same thing with the frame drag field that describes differential frame dragging. Build their integral curves of the eigenvectors. We call those vortex lines, taking the same word that's used in fluid mechanics. In fluid mechanics, vortex lines are the lines around which the fluid spins. In this case, they're the lines around which things twist in the following sense. This is differential frame dragging. Here is a blue tendex line. What this means is if this woman is oriented along that tendex line and she looks at her feet, she sees her gyroscope at her feet precessing in a clockwise direction. But her feet see a gyroscope at her head precessing in a clockwise direction. It's like taking a towel that's wet. You wring the towel out. If you let your left hand look at your right hand is, well, I guess we're wringing like this. Your right hand is twisting in a clockwise direction. When your right hand looks at your left hand is twisting in a clockwise direction. So we have clockwise vortex lines of twisting space. And the red vortex lines are counterclockwise vortex lines of twisting space. So this is the visualization of space-time curvature in terms of the forces they produce. Vortex lines that twist, tendex lines that stretch or squeeze. Similarly, the horizon vorticity is a normal component of this frame drag field. Again, it describes the twisting that would be felt by a person who is falling into the black hole with her body pointed normal to the black hole. And we have a horizon vortex as a region with large horizon vorticity, so strong twisting of space. There's a red or counterclockwise horizon vortex in the North Pole and a blue clockwise horizon vortex at the South Pole. And a three-dimensional vortex is a collection of vortex lines that have large vorticity, so very strong twisting. There's a clockwise or counterclockwise, that is red, a three-dimensional vortex sticks out of the North Pole of the black hole, and a blue clockwise vortex sticking out of the South Pole. So this is a little bit hard to follow because I'm moving quite fast, but it's basically very elementary. It's just the idea of, just very similar to magnetic field lines sticking out of the Earth. They describe twisting in this case, or stretching in the case of the tendex lines. Okay, now let's do something interesting. We will take two black holes, let them spin in opposite directions. So this black hole has a blue or clockwise vortex sticking out of its north pole, a counterclockwise vortex out of the south pole. This has counterclockwise north and clockwise south. I'm going to let these black holes collide head on. But we do not have good pictures of the evolution of the lines, just of the horizon, vorticity, and tendicity in terms of movies. So for a movie, I will just show you how the horizon vortex and tendex, how the horizon vortexes evolve. So the two black holes collide and merge. This is the horizon of the merged black hole. That's the point of no return. You fall through the horizon, you can never get out. We now have 4 vortexes sticking out of this black hole. We originally had 2, one on this black, 2 on this black hole and 2 on this black hole. Now they've merged. We have a blue one, and down on the bottom you can just see it, a red one and a blue one back on the other side. So 4 vortexes now sticking out of this black hole. These vortexes robustly retain their individuality. They continue to exist as individual entities. They're as physical as my arms. Just imagine my two legs and 2 arms sticking out of my body. It's the same thing. We have 4 vortexes sticking out of this merged black hole. And geometric dynamics is the dynamics of those vortexes, and similarly of tendexes. So I'm now going to show you the entire movie of what happens in this collision. I'm going to walk through it. So the first thing is the black holes raise tides on each other. Each one is pulling on the other, and the horizons develop pointed ends pointing toward each other, and then they merge. Now watch the upper right. We have a blue vortex of twisting space, of clockwise twisting space. The black hole pulsates. Suddenly the one in the upper right is red, then blue, then red, then blue. When these vortexes discover that there are 4, not just 2, they're happy to have 2 opposite types of vortexes. They will live there forever in a spinning black hole. When there are 4, they begin to interact. And as they interact, they exchange vorticity. One is twisting clockwise, the other counterclockwise. They interact, and they trade vorticity so that they go back and forth in direction of twist, oscillating from one to the other. And what is very interesting is what happens outside the black hole. So at a moment when this is blue and that is red, the vortex lines have now adjusted themselves. So you have blue vortex lines going out around from this blue horizon vortex back into a blue horizon vortex on the back side. Blue to blue. And this 3-dimensional vortex, the red one, goes around and goes back into the red vortex on the horizon. Now, in this oscillation, there is a moment when the black hole is green in my coloring. That means there is no horizon vorticity. That means these vortex lines had to come off of the black hole. They have slid off. The red ones have slid off and merged to form a closed loop. And the blue ones have slid off and merged to form a closed loop. And this is not an artist's conception. This is from a simulation. This beautiful picture is directly from the simulation. So this is a sequence of tori, donuts, rather like smoke rings, that consist of the vortex lines that were ejected from this vibrating black hole. With each vibration, when the black hole turns green, when the horizon vorticity goes to 0, the vortex lines are ejected and they wrap around to form a torus that moves outward at the speed of light. And as this vortex structure, as this smoke ring-like structure, this donut-like structure, as it moves outward, the dynamical motion generates tendex lines. that accompany it. And so as it moves out, once it is about one wavelength away from the black hole, it has strong Tendex lines that wrap around like this. The stretching Tendex lines wrap around like this. The squeezing Tendex lines wrap around like that. So you have a complicated structure, a donut, a torus, of interleaved vortex and Tendex lines. In fact, this locally, in the small region here, this has become a gravitational wave. The gravitational wave consists of a set of Tendex lines that stretch in one direction and squeeze in the other direction. But sitting on top of them, in the same region of space, vortex lines that twist counterclockwise or clockwise or counterclockwise. And that's what we have. There's 4 sets of lines in here. 2 sets of vortex lines, 2 sets of Tendex lines, and that is a gravitational wave. Now, more interesting is a collision in which these black holes are orbiting around each other. In that case, what happens is that these vortex lines, there were 4 sets of vortex lines. There were the red ones, there were 2 red ones and 2 blue ones. As the black hole, as the black holes collide and merge, these vortex lines then sweep out and back. Again, these are from a simulation. Sweep out and back like water from a turning sprinkler, or like spiral arms of a galaxy. And as they move outward, they acquire Tendex lines that wrap around and become gravitational waves. Here is, in more detail, an example where we have then, I'm showing you just 2 of the vortexes that stick out of the black hole. I'm not showing you the blue vortexes. Here are the vortex lines. Here is the vorticity in color-coded contour diagram. So strong vorticity. So it turns out the gravitational waves are being generated by these 2 vortexes in the near zone that stick out of the black hole, and similarly 2 blue vortexes sticking out of the black hole. As they turn, they generate the gravitational waves. The physical entity that produces the gravitational waves. Just like if I turn, my arms produce the gravitational waves. Here the gravitational waves are produced by these vortexes sticking out of the black hole. But when the black hole collision occurs, the merger occurs, there are also Tendexes stick out of the black hole in the near zone. There's a fan-shaped Tendex around the central region that stretches. I'm sorry, so this one squeezes. I have it drawn wrong. This one squeezes, and the ones at the end stretch. So there's a squeezing Tendex around the middle, and stretching Tendex is there. And as this merged black hole turns, due to the orbital angular momentum, these Tendexes trail out behind, and they produce gravitational waves. So gravitational waves are produced by the vortexes that stick out through the horizon and by the Tendexes. So here are the Tendexes sticking out of the horizon. So there are 2 sets of waves. They're the analog of electric multipolar radiation, electric dipole radiation, and magnetic dipole radiation. Radiation produced, gravitational waves produced by vortexes that stick out through a black hole and by Tendexes. Remarkably, when these 2 types of waves beat against each other, that beating can produce, we're having some trouble here with it. The beating can produce a very anisotropic momentum flow in the gravitational waves, giving rise to a large kick. So the merged black hole can receive a kick as large as 4,000 kilometers per second, which is enough to eject the merged black hole from the nucleus of any galaxy. Now, to indicate how strong the vortexes and tendexes are, let me show you a simulation of a black hole and a neutron star in orbit around each other. They're orbiting in this plane. The black hole is 3 times larger mass than the neutron star. It's only slightly larger physically. The black hole is spinning around this axis. And so it has vortexes that stick out of this polar region and that polar region, and tendexes that stick out of the black hole. The tendexes sticking out of the black hole will take the neutron star and pull it apart. Then the vortexes will take this nuclear matter, it's still near nuclear density, the neutron star has been torn apart, and throw it up into the plane orthogonal to the spin. So the tendexes tear the star apart. The vortexes throw all of this stellar material up into a new plane, 1.5 solar masses of nuclear matter. So here's the neutron star going around. It's starting to be torn apart. It's being thrown up into this new plane. And this process will produce gravitational waves. When the neutron star is torn apart, a strong burst of gamma rays, strong burst of neutrinos, as the hot nuclear matter from the core of the neutron star is opened up for the external universe to see. This is the foundation for what we call multi-messenger astronomy. Each of these we can think of as a messenger that brings us information about what's happening, the gravitational waves, the gamma rays, and neutrinos. Let me pause and ask if there are any questions, because I'm going to spend the rest of my time talking about gravitational waves then and multi-messenger astronomy.